Good evening, ladies and gentlemen. I'm Lakmini Abesurya from Building Services Engineering Sectional Committee. I welcome you all to the second webinar organized by the Building Services Engineering Sectional Committee for the session 2019-2020. Thank you all for taking your valuable time out and being here with us today. We started this webinar series after a short break of 3 months due to COVID-19. Though we were silent for a while, the Building Services Engineering Sectional Committee didn't forget our part in defeating COVID-19 and actively contributed for two important national level activities. We have successfully completed the renovation of mechanical ventilation and air conditioning system of the ICU complex at IDH Hospital in collaboration of Sri Lanka Navy. Mind you, our engineers carried out this renovation inside the hospital at a time this is the last place anyone wants to be around when corona was in peak. Moreover, our committee contributed in developing the national COVID-19 guideline along with the Ministry of Health, the World Health Organization, and few other organizations. Out of 46 technical experts who contributed for this guideline, there were only 5 who were not from the medical background, and I am proud to say that out of those 5 members, 4 were from our Building Services Engineering Sectional Committee. Going back to the lecture, our guest speaker today is Dr. Senaka Dharmatilaka, who will be talking to you on engineered facade design for modern high-rise buildings. In high-rise buildings, facade design criteria is not limited to the visual aesthetics, but also to its performance in buildings dynamics. Today's focus is on parameters in which the facade type is selected and the importance of those parameters in design considerations. Now, let me introduce our speaker tonight, Dr. Senaka Dharmatilaka. He obtained his bachelor's degree as an architect in built environment from University of Moratuwa, followed by a master's in architecture from University of Moratuwa and a PhD from School of Architecture in National University of Singapore. He also holds a postgraduate diploma in international affairs from Bandaranaike Center for International Studies, Sri Lanka. Dr. Senaka serves in the capacity of Chief Architect with Overseas Realty PLC, Mireka Capital Land, the developer of Havelock City Mixed Development Project, which comprise 1,000 plus condominium apartments, a 50-story office tower, and a 6-story shopping mall. He completes 15 years of service in this project since its inception. Moreover, he serves as a visiting lecturer at the City School of Architecture, Colombo, and at the Department of Architecture in University of Moratuwa. Ladies and gentlemen, without further ado, please join me to welcome our speaker tonight, Dr. Senaka Dharmatilaka. One special announcement. Please note that we will be running a live Q&A session at the end of the presentation. You may mute your microphones and videos until then. While the presentation is going on, you can post your questions to the moderator through chat. You can find the option at the bottom of your screen if you're logged from a laptop. Depending on the time, we will direct your questions to the speaker at the end of the presentation. Now, let's move to the presentation. Over to you, sir.
Thank you. Thank you, Lakmini. Hi. Well, it's always a pleasure to meet our engineers of what I would call the closest fraternity of allied professionals related to the field of architecture. Well, we have structural engineers, civil engineers, mechanical, electrical, and plumbing, all fields, including electronics, which are all of which are closely related to the subject of facades, right? And and talking about the fraternity of engineers, I'm always indebted, as well as I talk with fond memories of most professionals related to your institute, such as some of my teachers, like Mr. Ferdinando of what do you call the engineering the SEC or State Engineering Corporation. Well, Mr. Upasena, from whom I continue to learn, as well as distinguished engineers in our midst, such as Mr. Sarovira Surya, Mr. Sahabandhu of CCB, industrial giants in the industry such as Mr. U.S. Karunaratne, well, talking about giants, engineers such as Mr. Samita uh, Jayakodi, giant in the field of not only in terms of knowledge and expertise, but even in physical appearance, so to speak. And last but not least, I need to thank the organizing committee of this event, Mr. Prasanna Narangoda, who's with me in my capsule. And then I have Mr. Ishan at the control center, Houston. So if there's any problem with the technicalities, all I have to say is, Houston, we do have a problem. So I don't see a problem right now. So let's move on to the with the proceedings. Let me share the screen with you. Right. Okay. Why do I see? Hey, okay. So, talking about high-rise buildings and building facades, especially about building facades, I must say this is a very specialized field, and we do have facade engineers, glazing engineers who are related to this field. First, let me start with a confession. I am none of them. I am not a facade engineer nor a glazing engineer, and I wouldn't call myself an expert or a specialist in this field. But what I am going to do today is share my experiences and also voice my opinions as well as views, and also share some of my fears and anxieties related to the development of this science of facade engineering, and maybe in my own humble way make a contribution to initiate this field of facade engineering, which should come from the engineering fraternity, right? So please bear with me. It is not an expert lecturing top down, but one of your peers or even an observer from an allied profession who's giving his views to upon a field which we will need to develop together. So talking about the functions of a facade, there's no better place I would think would be more appropriate than talking from the Shanghai Bund, looking across the Huangpu River into the spanking new skyline of Pudong area. I think you can see the buildings on the other side. I'm seeing a little red line coming on the screen. I don't know whether it's right. Okay, I think it's something that falls on my screen only. So you can see at the time of capturing this photograph, I think it's somewhere around 5 years earlier. And at that time, if you look at the profile of buildings across the world, you can see 2 of the top 5 buildings, the Shanghai Tower and the IFC Tower, International Financial Center Tower of Shanghai, are among this singular frame or singular skyline. So you can see that this frame captures 2 of the top 5 high rises in the world at this point of time. So what does what are the functions performed by a facade? The obvious function, so to speak. One is, of course, it generates a building form. It gives form to a building and it articulates a visual expression. If it's a company, it gives corporate identity. It ensures visual privacy where necessary and permeability where it's needed. so that you have the degree of privacy that you want to enjoy. Then it also ensures that water does not penetrate, and it protects you from the weather elements. It ensures that uh, air impermeability, or there's no permeability of air through the skin, so it acts as a skin. It resists the wind together with the building structure and ensures that the occupants are well insulated from wind movement. It resists the thermal variations outside, so it enables you to create your own microclimate inside. And also it helps to insulate you from the hustle and bustle of the street or the noises around. It gives you acoustic insulation. Talking about facades, you can see on the left hand, from the left hand side to the right hand side, you can have the most expressive, provocative facades up to the most mundane and the most unassuming ones. But the structural system or the facade system adapted could be as complicated as the most complicated looking facade, although the structure looks unassuming and or mundane. Now, on your left-hand side, what you see is Mr. IMP's Bank of China building from in Hong Kong Central, right, where it stands proud overlooking the Victoria Harbour. Well, coming to another example, the at the bottom right-hand corner is the IFC Tower of Hong Kong. And what I'm trying to explain by this slide is that when a professional, an architect or an engineer, is commissioned with the task of deciding on a facade, so many models or so many methods or strategies are looked at, explored, evaluated, discarded, then readapted and adjusted to suit situations, debated intensely in terms of the technical possibilities and also the, the architectural expression and so on, and etc. But at the end of the day, once the facade is done and dusted, it's all just it's all covered up and nobody talks about it anymore, right? So everything that went on to that you see does it come on this one? No. Okay. So now this is the final product, the ground level of the IFC building in Hong Kong. And what are the performance characteristics that you want to ensure by a facade? Of course, the three main performance characteristics would be the infiltration air, the penetration of water, and the deflection of the structural members of the facade, such as the mullion as well as the transoms, which are the main elements that take that check and balance the deflections that that affect the facade. Now you can see the transom, which is the horizontal member, the mullion, which is the vertical member. Then you'll have the pressure plate, which ensures that the glazing infill is secured onto the transom and the mullion, and of course it is supported by an EPDM setting block, and the pressure plate and the glazing infill is at the interface with the weather. It's taken up by an EPDM gasket, and all of it is at the end of the day covered by the pressure plate covers, right? And moving on to an experience, more recent experience of checking these parameters such as air infiltration, water penetration, and deflection. This was conducted about a few months ago in Shenzhen, where we wanted to check the design, the window structure, so to speak. I wouldn't call it a curtain wall, but of course the glazing structure in terms of its design and fabrication as well as the components used. So here the testing is a bit intense, you use wind turbine to simulate the design pressure, or even beyond the design pressure, the designed wind pressure here we adapted as 4 kPa, kilopascals, or 4000 pascals. Of course, in this part of the world, commonly it's 2.5 kPa or 2500 kilopascals is used. But we were adapting to be on the safe side. We adapted the Hong Kong standards of wind pressure, and for that you have the once you mount the glazing structure, the entire formation on within a compartment, an enclosed compartment through which you go. You can see the doors are open, and the apparatus that ensures wind penetration is seen there. So this is a view from within the compartment, where you see the gauges that the gauges which would sense the deflection of these mullions and the transoms could be transmitted to a control room nearby, and here you can monitor the quantum of air penetration as well as the deflection of these structural members, and then the software itself would ensure that they remain within permissible standards. Now here within the structure we have our engineer Mr. Jivananda, a member of the institute as well. Always I feel very safe with Gio Malli, because he is very thorough with his checking and ensuring that these deflections as well as penetrations remain within parameters, right? And first, this is the preliminary inspection to see whether the gauges are in the correct space, the correct locations, and in the correct positions, and to see whether the joint fields are perfectly done. And once this testing is done, he would move on to the control room. Then, instead of using positive pressure of 4 kPa from outside, negative pressure of -4 kPa would be, so it will be, the room would be made into a vacuum, and that would by making the chamber minus 4000 pascals, you will gauge the deflections of the mullions and the transoms, and also the amount of air infiltration. So these are this is the control room, and the warning signals will come out if these parameters go beyond permissible values. And these are the apparatus at site. Still the turboprop is not engaged. Then the size of this is an image just to show the scale of the chamber. The three of us can very comfortably fit within across the chamber on the side of the width, and that's the size of the wind turbine. Then there will be the nozzles at the designated spaces. The spray rack will come into play and start simulating rain conditions, or to see the first. It will be the static water penetration test with the negative pressure. Then it will be the turboprop will start operating, and then you will see cyclonic conditions created. So to check the functional validity of the EPDM gaskets, the beadings, the sealants, the backer rods, everything now has to kind of be coming to an orchestrated play of ensuring air and water infiltration through the building skin or the facade. At the end of the day, at the end of the test, later on, of course, after going towards even 1.5 times the working pressure or the design pressure, 6,000 pascals, you will test whether any permanent deflections are observed in the members, such as the mullions and the transoms. Then Mr. Jivananda will come in again and then check whether any water has penetrated by visual observation, and check the mullions and the transoms for any permanent deflections, whether they are within permissible values. And then at the end of the day, we will get these people to dismantle the entire fabrication piece by piece, just to ensure that no fraud has happened by where stiffness is increased by the insertion of steel rods or steel elements into the aluminum channel. Now, this is all about the performance testing. And what what are the parameters which are tested? We said infiltration, which is possible through the joints and gaskets between the horizontal and the vertical mullions. We call them horizontal and vertical, but of course the horizontal members are called the transoms, right? And then the verticals will be the mullions. And not only the gaskets and joints, the weep holes and the sealant joints could also allow air infiltration. So what we test here is the integrity of the composite assemblage or the composite assembly. Of course, there are standards specifying the acceptable level of air infiltration, which is given in terms of cubic feet per minute per square foot at a given test pressure. I can vaguely remember when we were studying, I can remember the permissible amounts were about 0.06 CFM per square foot at a minimum pressure of 1.57 PSF. But of course, I wouldn't rely on my memory and the validity of these at this time and age. I'm sure the glazing engineers would specify the exact level of air infiltration in terms of the given assembly and so on. And then we come to water penetration, and it's about water penetration is about ensuring no water is penetrated into the interior of the building from the exterior. Of course, we could allow for controlled water penetration beyond the innermost vertical plane, which stands between the building user and the exterior. But it's a design like the car door, right? Like the car, you could allow a certain amount of water to be taken in the layers beyond the car cabin, but it has to drain back to the exterior eventually. And you have to ensure that there's an effective system for that. Well, what we saw earlier was the design testing before the installation or the fabrication happens, just to test the integrity of the design as well as the components. But once these things come into sight and when the actual installation happens, then you come in with the spray rack test, where you use sometimes with positive air pressure or even the nozzle velocity itself, where the spray rack and the nozzles are specified, pre-specified, where the location of the nozzles as well as the velocity with which it throws water at the joints, specifically the joints between the mullions and the transoms, where the EPD and gaskets would be preventing water penetration, and the duration of the test is also specified. So you have to engage the spray rack to a certain period. Each spray rack has to test each the designated joints at a certain velocity of water discharge to a certain degree of certain amount of time. And of course, even the distance between the spray rack and the window assembly has to be predetermined so that you know the exact pressure at which the water will be sprayed at the critical joints. So then comes the other part, deflection. Now, one thing about deflection is we use aluminium as a common material for our glazing. And the problem with aluminium is the modulus of elasticity, so to speak. So it is about 1/3 of that of steel. To be precise, it ensures that it deflects 3 times more than steel, or 3 times compared to steel. And these deflection limits are also specified. You have perpendicular deflections which are wind induced, or in plane deflections which are
there are some lines.
Excuse me, I think the screen is accumulating some lines on there are some lines appearing on the screen. We will try to see how we could delete these lines. So bear with me for some time while Nara Mali will help me to kind of. Mikael. How did these lines come? Mikael. For a moment, we will stop sharing the screen and we'll be back in a moment, right? Hold on.
Yes.
Okay, welcome back, so to speak. Right. So, well, always the technical glitches. Well, that makes life even more interesting, I suppose. So, I think where were I? deflections, right? So you're talking about the modulus of elasticity in aluminium, which makes it uh, compared to steel, which makes it deflect 3 times more than the deflection in steel. And of course, deflection limits uh, are set in terms of perpendicular or wind-induced deflections, or in plane, or else what we call dead load-induced deflections. And what can a deflection do? A deflection can either break the glazing infill, break the glass, or else the glazing infills could be ejected off the mullion components, both of which cause damage, and then it defeats the purpose of the facade, right? And also deflection needs to be controlled to ensure that the 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 movement of the curtain wall interior is uh, controlled. I mean, what good is a curtain wall uh, or a building scheme that keeps bobbing in and out of the architectural interior? Then the the deflection limits uh, should be agreed upon earlier, or else should be prescribed by the glazing engineer, and then it should be observed. I can vaguely remember the deflection limits were set, I mean, as a thumb rule, as the distance of a mullion between two joints divided by 175. Of course, you need to check the current deflection limits set in the modern industry practice. But of course, this we used it as a thumb rule, right? And then the depth, if you take the depth of the curtain wall or the thickness, is also controlled by the need to keep the deflection limits at bay or within the specification. So these, if deflections are excessive, and if you need to maintain the same thickness for visual reasons of the mullions and the transoms, then what you do is you introduce steel reinforcements added into the mullion tubes, so that gives extra stiffness. Of course, the fourth characteristic I talk about is related to strength. It refers to the maximum usable strength, not looking at the stiffness that mitigate deflection, but rather like the Japanese term judo, which means strength by pliability. So even deflections are also taken in as permissible values in this parameter. Having looked at those characteristics or the test parameters, let's look at the common facade types. So the common facade types now used, the most predominantly used ones will be the windows and the solid wall, which is seen in the right hand side of the screen in a building that overlooks the Victoria Harbour in Hong Kong Central, designed by Mr. James Kinoshita. And then you have the curtain walls. The curtain walls also do have two types, the stick system and the unitized system, right? Stick system and the unitized system do have differences in terms of installation and the assembly of components in sequence. Now, looking at the windows and what you call the solid wall and the windows, here again I look at the Jardine House building designed by Mr. Kinoshita. Uh, one of the most senior architects at Hong Kong Uni, he would explain how these punch windows, which look like portholes. We thought it was because the building was looking towards the Victoria Harbour. He wanted to make a gesture related to navigation. No, but the engineers and the architects got together and decided that circular punch holes would ensure minimum damage to the structural integrity of these shear walls. So that's how the circular windows came in. Next to this building stands another building which gives a very provocative expression, Bank of China building by Mr. I.N. Pei. And this, many people would assume that it's a framed, bundled it's a bundled frame tube structure, but actually it's the same frame tube structure which is folded inward and outwards, and you can call it an external frame tube structure. Of course, in terms of the principle, the glazing infills are mere infills between the structural frame of the facade or the tube, the external frame of the tube. So it could be also categorized along with the window and a solid wall structure. The next one is the curtain wall. Now the curtain wall is defined in terms of its structural relationship with the main concrete structure, whereas the solid wall and windows, the glazing infill will stand solidly or squarely on the perimeter slab edge perpendicular to it. Here we would find that the curtain wall is held as an external element and attached externally to the perimeter slab edge on the external vertical surface. As you see here, it's the anchor. It's the anchor that takes the vertical as well as the perpendicular loads. Whereas in the window and the solid wall, the window would stand on the perimeter slab edge, and the concrete slab would perpendicularly directly take the load of the glazing element or the facade element. Now here it's the anchor that takes the vertical as well as the horizontal loads. Let's look at different types of curtain walls. You have the stick system, which is the transoms and mullions being fixed first, and then comes the glazing infills. Then the unit panel system, where the different units are brought to site. Then you have hybrid systems, like you have the units as well as the mullions. The mullions will ensure that units are checked against lateral movement. Then you have point fixed glazing systems, point fixed curtain walls. Also you have, which is seen here in the image above. And of course, this kind of structure, I would rather call it what you call as a shop front curtain wall, since it stands between two structural elements. The glazing the glazing sits squarely on the horizontal surface of the receiving slab. So the curtain wall systems, as I emphasized earlier, the stick system, where it's where the components are assembled piece by piece at the building site. First the mullions come in, then the transoms come in, and then the glazing infills are installed. So it's actually it's the mullions that take the main load, and then the transoms will be secondary elements on the mullions, and then comes the glazing infill. So the transom, the anchors would take the entire load. That the anchors would take the entire load of the mullions, the transoms, as well as the glazing. Unitized system comprises of completed panels which are fabricated elsewhere, brought into site from a factory, installed after it comes to site. So you can see the size of the curtain wall will depend on the floor-to-floor height of the building, or where the anchors could be located. So it's almost like hanging a picture frame on a wall, right? Of course, in a bit more complex system of fixing. You can see again unitized panel here on the left hand side, where the panels are fixed directly onto the, or hung directly on the anchors, which are fixed onto the floor slab of the concrete structure. Then on the right hand side is the stick system. You first fix the mullions, then comes the transom, and then comes in the glazing infills. Now these are two images. These are images of the stick system. You can see the stick system. First, the skeleton is made. You can see the mullions fixed by the anchors. Then comes the transoms, and then slowly but steadily the glazing infills come. You can see a detailed image of the anchor there, which secures the mullion firmly onto the perimeter slab edge. And then, of course, the good old unitized system where the entire unit is brought in like a picture frame and then literally attached or hung on the slab edge on the what do you call on the uh, anchors which are mounted on the perimeter slab edge. So it could be on the horizontal surface of the perimeter slab edge, which gives you a better assurance that it won't be dislodged, and the stresses are much easily distributed onto the concrete structure. Well, talking about curtain walls, so because I think I will dedicate more time onto the curtain wall, since this is something novel that is coming along with most of our high rises now. Being a curtain wall is not that easy, because just like human relationships, it's the relationship with the main structure. So it's a very complex tango that the curtain wall has to have along with the main structure. Why? Both of them have to move together, and each of them move in different ways. Now it's almost like human relationships, right? So coming into the finite details of the curtain wall and the main structure relationship. If you look at a curtain wall, now you see the joint there, the anchor. The horizontal loads are transmitted through the connectors at maybe at the floor as well as the column. But the vertical loads or the dead loads of the curtain wall will be directly from the anchor. It will be right. So anchor, which is on the perimeter floor slab, right? And then what are the movements that the curtain wall has to make along with the main structure? The first, the wind induced sway. The main structure sways according to wind, because the slenderness ratios are low and in high rises. So with the wind, the taller you are, the more you sway, and the curtain wall also has to move along with the main structure, and it has to resist the sway. So it has to be flexible, right? And the curtain wall also has to resist the thermal movements against the main structure, right? Or the thermal expansions and contractions. The two different materials, mainly the aluminum of the curtain wall will, and the concrete of the main structure will expand and contract in their own manner. So these differences will permit differential movements. So this difference of movement also has to be absorbed by the flexibility of the curtain wall. So it has to be a rather a loose joint, so to speak. It has to allow for twists and turns. And the curtain wall also has to resist the seismic forces that affect the main structure. Of course, fortunately, we don't have certain seismic loads that are or the subterranean movements that cause the main structure to move. I think in countries like Japan, you'll find it a bit more. And while allowing these movements and being flexible, it has to resist again air and water infiltration, right? So you have to be airtight and watertight while allowing for flexibility, right? So flexibility should accommodate relative movements with the main structure, and you have to be rigid enough to withstand air and water infiltration. A typical tall order that is that may be given to a student or an employee, certain things like you have to be confident but not arrogant, and you have to be you have to have self-awareness, but you should not be self-conscious. So the student would always say, yes sir, but it's a tall order, isn't it? So the problem of the curtain wall is that it has to be flexible enough to allow relative movement and rigid enough or compacted enough to ensure air and water infiltration. Now, at the same time, you have to have effective fire stops between floors. Now, that is another order that comes from the idea of fire compartmentalization. So you need to ensure that the fire from the flame and smoke does not migrate from the engaged compartment to the compartments above. So the building joint, being a fire stop, has to have these connections of the curtain wall with the structure should ensure an effective fire stop between floors. But at the same time, again, it has to be flexible enough to sway or move against the concrete structure. Now that is quite a tall order. Let's see how this can be accommodated, right? So at this point where you find the building, the anchors, you can see how the anchors are done in a funny manner. Let's see how these anchors behave. Now these are little tests of allowable parameters for building sway and how the curtain wall has to allow for these uh, relative movements. Now this is quite straightforward. If you look at this, this is the back and forth movement. So when the main structure moves back and forth, this also has to allow this movement between the main structure and the curtain wall. But what happens on the sides, the perpendicular side, you will see you have a problem called interflow plate drift. The interflow plate drift would require the glass to behave in a very awkward manner, where the frame has to be oblique. Now that is very difficult to do, right? Now, in order to take into account all these, the joints have to ensure, just like the vertical movements of the thermal expansions could be accommodated by slotted anchors. The anchor would allow up and down movement. Then you see how the sway, the up and down movement, then the sway from side to side will be allowed from embedded parts, which allow for sway sideways, and then the slotted anchors on the perpendicular would allow back and forth movement. So you can see how the curtain wall could move on all three axes, up and down, side to side, back and forth, etc. Now, we talked about the the requirement of fireproofing, or the problem of the curtain wall in ensuring the role of a fire stop. Now, perimeter slab edge, which is called the slab, this is the floor slab, and this is the curtain wall, and this is what you call the perimeter slab edge. Now, the perimeter slab edge always has to be a building joint. Why? This is the gap between two fire compartments, the floor above and the floor below, right? So you are not supposed to allow fire. So these fire stops need to ensure fire compartmentalization. So this is to ensure that the flames and smoke does not migrate up to the upper levels between this perimeter slab edge joint. So the commonly used material for this is rock wool, which is compressed 25% in terms of by ensuring 25% compression. So commonly what they do is they get a 125 millimeter thickness thick rock wool segment and ensure it is squeezed into a cavity of 100 millimeters. Although it's not mathematically exactly accurate, that works, and then people are quite happy with it. And of course, the rock wool is good to prevent flame migration, but not smoke. Smoke can traverse through the rock wool, although it's compressed. So you need to have what you call top caulking. Sometimes you use silicon, and whatever you use, the top caulking has to be done by a good fire stop sealant, right? So this is what you call, where I call top caulking. The rock wool insulation, and of course I'm looking at a rigid insulation as well in what I call the spandrel area. Let's go to it in the next slide. Then another thing, just like the perimeter slab edge which is needed to be a building joint, which has to become a fire stop as well. Then comes the rain screen principle. The rain screen principle, very simply, is for double skin facades. Now, rain screen principle ensures between the two facades of the building skin. The guy who gets engaged severely for water penetration is the outermost gasket, right? So in order to prevent water infiltration through the outermost gasket, what this principle does is, through a weep hole which is articulated so well so that water doesn't penetrate, it will ensure that the pressure on the outside and the inside of the outermost gasket is equalized. So it is called equalizing the pressure within the glazing rebate, or the gap between the two glazing planes. And this glazing rebate, by ensuring that there is controlled ventilation between the two glass planes. So this glazing rebate between the inner and the outer gasket would ensure that there's no substantial pressure exerted on the outermost gasket of the water to come in. And these weep holes that ventilate the rebate should be articulated well to prevent water penetration, which I will show you in the subsequent slide. I think this is the more theoretical diagram, which shows the pressure equalization by the weep hole, but this is the more practical diagram which will show the outermost gasket, which all of course becomes an EPDM gasket in reality. And in order to equalize the pressure on the outermost gasket on either side, this weep hole will allow air to come in and fill this pressure chamber, and so that the pressure at this point and this point are same, and the water penetration is checked. So it's the inner gasket that takes the pressure, the air pressure, and prevents the air from penetration into the building. So this is the range principle described as simply as possible. But of course, there are much more complex methods of looking at it and articulating a frame. Now, of course, just to kind of show you what these weep holes are. These are the weep holes which are exposed. Of course, in reality, what we do is we have weep hole covers. Individual covers will come in, neoprene covers will cover these, so that there's no the beating rain coming in horizontally will not be allowed into the pressure chamber. Now, then talk about loads that that act upon a curtain wall. Now, the transfer of loads happen at this point. So all the imposed loads of the curtain wall, whether it's horizontal or vertical, are transmitted through anchors such as these, which are attached to the mullions, right? So the mullions would transmit all these to the main structure through the anchor here. So these are the anchors that we see. And these, one of the main loads will be the dead loads. Of course, the dead load is the weight of the curtain wall itself, the mullions, the transoms, the sunshades, etc. And of course, not to mention the glazing infills, right, which come up with a substantial weight, which has to be carried by the main structure. Then the main thing is the wind loads. So the wind loads could be direct wind, could be the direct wind pressure on the glazing infills, or even the aspects such as vortex shedding, which cause severe stresses on the structure, as well as especially the curtain wall. And to identify the pressures exerted, and to kind of ensure that the sections are designed accordingly, you do wind tunnel studies like what you see here, right? Or CFD modeling, which is called computerized flow dynamics, which can model the amount of pressures that different part of the curtain wall structure has to undergo. So even the glazing infills as well as the structural elements could be designed accordingly. Now, not only vortex shedding, you can see how the wind blows faster according to the building form, right? At the flanking edges as opposed to the directly perpendicular edges. Here it will be a wind shadow, and this will be a huge shaft of velocity of wind going through, and good old Uncle Bernoulli will come in and show how the more the velocity, the pressure drops. So the glazing infills are sucked out of their sockets from the high pressure zones within the building and out into the low pressure created at the exterior. Now, this modeling should not only consider the building itself, but you can see you need to take the surrounding context. And the surrounding context may not only be limited to the existing buildings, you need to kind of get the buildings in the pipeline. What do you mean the buildings in the pipeline? If you take an urban area, especially like Colombo, growing fast, you need to forecast the buildings that are going to come, especially the high rises that will come along within a period time horizon of 5 years, 10 years, or 15 years, in order to see how this new member that we are going to introduce in the community of buildings will have compound wind loads depending on the wind corridors created, tunneling effects created between the buildings, and so on. And not only the immediate context, but the general macro context should be represented at least in terms of flow dynamic considerations by introducing different types of what you call resistance nodes. Resistance modes of different types show how maybe depending on the topography of the land or the buildings which are there, the building forms, the morphology of the city around, how the wind rises or drops in the macro context. And then the micro context will be the surrounding buildings in the locality, especially the street on which the building is, and also in the surrounding area. Then when it comes to these are examples of the wind tunnel, and these are the CFD, the computerized flow dynamic would show in different color coding what are the high pressure areas in terms of red and orange, and then the low pressure areas will be seen in the greens and the blues as and when they recede away. And this would help, just like just like the wind tunnel test, where you insert certain sensors and then get the readings. Uh, and of course, one thing is about this is also the wind tunnel could be rotated. What you do is in terms of this testing against a certain wind load, you could see the periodic shifts in the wind in that locality, whether it's the southeast monsoon or the northwest, or whether it's the southwest monsoon or the northeast. That also could be seen in terms of the direction the wind comes in by simply rotating the model, right? CFD also allows that. Of course, being a computer modeling, you can do any amount of directions, combinations and permutations of the wind conditions with the velocity, the changes in velocities, changes in direction, and even the hard part that you have to do with resistance mode in creating a wind tunnel test could be easily done in terms of 3D modeling. But of course, although I say it's easier said than done. People have to really break test for a couple of days in order to make these 3D models and before you do the proper testing, right? So these are examples of 3D modeling, and looking at how the model would change its shape along with along with the crosswind, along the wind, or how torsion takes place, and how the structure twists and turns against the curtain wall, and how these relative moments has to be resisted. Then the other one is about the seismic loads. We talked about it, and the wind-induced building sway. So this has to withstand the sway by the gap between the building infill and the mullion we talked about, right? And how do we allow for this relative movement? Of course, these are merely thumb rules. You need to take it with a pinch of salt, because there was a time when we were looking at 75 millimeters as the comparative gap that could allow this relative movement between the curtain wall and the main structure to allow sway. But of course, you need to consult the glazing engineer to come up with the proper limits prescribed for that particular application of the wall, because there could be different needs depending on different usages of the buildings and also the client requirements. And you can see how these the anchors are designed to ensure movement sideways, back and forth, and of course the there will be movements allowed in terms of the top and bottom movement also in terms of the mullion joint. These are just images I flicked from a work site of a friend of mine. And then we come to the thermal loads. Now, in terms of the thermal load, as much as the modulus of elasticity, aluminum has a relatively high coefficient of thermal expansion. So it contracts and expands and contracts within the span of few floors. So it could expand and contract. Right now, so the horizontal, so in order to resist these contraction and the expansions and contractions, the transoms are cut a bit short where they meet the mullion, just to ensure there's a slight gap between the mullion and the the vertical mullion and the horizontal transom. Now this also allows a little bit when you fracture the EPDM gasket, it allows a little bit of what you call the range screen principle to come in, which I will explain later. So in unitized curtain walls, these gaps are kept deliberately, and the air water penetration is mitigated by what you call wiper gaskets. So vertically, the anchors would carry carry only the wind loads, will be slotted to allow movement, like what you see here. The anchor is slotted so that the vertical movement up and down of this mullion is allowed, right? And this also allows the live load deflections of the perimeter slab edge and the creep, right? So not only the thermal expansions and contractions of the mullion, but little deflections of the floor slab also could be absorbed by that. And another way, and another mechanism is, now you see the anchor there. Now the other flexibility you could get is the telescopic joints between the mullions, right? So you can see the joint is done one into the other, so it's rather the joint is telescopic. It allows a little bit of vertical movement relatively between two mullion sections. Talking about the loads that act upon a curtain wall, this is something that we hardly experience, the snow loads. Of course, you need to be careful if your curtain wall slope exceeds 20 degrees, right? So just like a roof, if your curtain wall, especially this happens in the penthouses, or the uppermost lounges in high rises where you have palisaded roof coming down at angles which are less than 20 degrees, then you need to ensure this snow load is also taken into account. Then of course blast loads that we also have been concerned with, and especially Singapore, the SPE was conducting certain tests alongside the FBI on how to ensure blast resistant glass. Now, of course, bulletproof glass is laminated glass, we know, but we need to ensure that the entire laminated glass panel does not get segmented or detached from the frame and then hit then hit an innocent inhabitant and then kills the guy off. Now, in order to do that, experts have developed ways and means of ensuring that the glazing infill doesn't detach from the frame, glass frame, maybe the mullion and the transom frame maybe, or if there's a different frame that holds on the glass, that frame also has to be secured even if it flies off with the frame, that could also be fatal. So you need to make sure that from the point you attach it to the main structure, the frame, the glazing infill, the gaskets, everything stays compact as one cohesive structure. Now, talking about the blast loads, of course, we need to talk about the infills, right? So coming into the infills of the curtain wall, I think these panels which are inserted to the wall in between the mullion and the transom, the most popular one is glass, right? That's why we always call it glazing, although sometimes the glazing, we use the term glazing, sometimes the infills are of different material. Now, glasses, actually, although I have written here, the glass types start from anneal glass or float glass, which is the glass which is melted and smelted on a bed of molten lead. So that's why you call it float glass, because the glass is floated in the process of annealing on a molten bed of lead. And the next step is heat strengthened glass. By doing the secondary heating process, this is strengthened, but the strength is about twice or thrice, maybe about thrice at the most than the anneal glass. But the better type of safety glass will be the fully tempered glass, which goes through a secondary process of annealing, which melts the glass until and systematically quenches it, so that there's a little membrane or a crust forms around the glass content while the interior is molten, and it's of course creates certain stresses within this substance, but it is about 6 times stronger than the anneal glass. And the other advantage is it shatters into small pieces, cubes, and ensures the safety of the people inside. So unless if the glass does not shatter into very sharp edges and cuts through the skin and so on, whereas the tempered glass will break the glass into tiny trissels and at a greater impact, that is that could be which is much superior than the anneal glass or heat strengthened glass. Then in order to even prevent the crystals from flying around, we have tempered laminated glass, and the lamination is always done with an elastic membrane. Normally you use PVB or use polyvinyl bonding. The stronger one is called SGP. It's a trade name called Centiglass Plus, but it is much stronger than the PVB, and also for areas where the laminated glass has to be exposed to weather conditions, water and heat and sunlight. Always the prescribed type is centri-laminated glass, because otherwise the PVB delaminates when it is exposed to weather elements for prolonged periods. So the SGP lamination is important for open-ended laminated glass panels like canopies. You have glass canopies coming out now, or even glass handrails. I think various clients like to have glass handrails in open air spaces as well. So then you need to be very careful of the type of glazing you use. Then you have the double glazing or the insulated glass, which has the 2 panels of glass with a spacer which is 12 millimeter standard, and inside is filled with either atmospheric air or inert gas. Now this is good for sound and heat insulation, way better than the above 4 or 3. But the problem is most of the time in the double glazing, it's 2 panels of anneal glass which are used on either side, and if it's subjected to shattering, it will break off just like the normal anneal glass, come up with sharp edges, damage the inhabitants and so on. So when you're selecting this, it's always a counterbalance. It's always a trade-off between the properties that you want to have in this in the glazing infill, right? Whether it's going to be the green elements of energy consumption or sound insulation or safety, right? Safety against impacts especially. And then you have the low E glasses. Low E glasses could be composite glazing, if you are not having the low E coating on the tempered glass, the recommended is to have it within the tempered laminated glass. Then you need to decide on which surface the low E coating comes. Recommendedly on the third surface, so to speak, because the glazing would have 4 surfaces when it's tempered laminated glass with low E coating. From inside, once you start count, you call it the third surface. So the innermost surface of the inner glass, outermost surface of the inner glass, then comes the laminated, the PVB, and then the third surface will be the innermost surface of the outer glass. So that's where the low E coating comes ideally, so that it's protected against weather elements. But you need to ensure that the low E coating is compatible with the lamination that you use, either PVB or SDP. Otherwise, we'll have a problem of incompatibility. Then, of course, leaving aside glass, we have other infills like stone veneer, which is called granite, marble. You have travertine, it's a sedimented stone, especially coming from Italy and Turkey, or limestone. Then we have even fabric veneer. You have panels of aluminium or aluminium composite panels. And especially if you are using aluminium composite panels, you have to be very sure. If it's high rise, you need to ensure that inflammability is ensured there, because aluminium has a very bad habit of melting away. And then although aluminium is non-combustible, the infill in most of the composite panels that you have here is the HDPE, high density polyethylene, which is highly inflammable. It catches flame like nothing on earth. So for the regulation in developed countries is either the ceramic infill or to have fire retardant infill within the aluminium composite panel. Then you can have FRP or terracotta, etc. It could be FRP, that's fiber reinforced plastic, FRC, fiber reinforced concrete, or FRG, fiber reinforced gypsum. But of the FRG is very much good for interior use, not for exteriors. FRP and FRC are recommended as panels on curtain walls. Of course, for the MEP areas where you need air infiltration, you need to have doors. Then windows and vents are also there, especially for fire access, and mostly recommended only for fire access panels when it comes to high rises. Why? Because these fireman knockout glazing panels are needed when you can't enter from the ground floor, right? So you could use them for venting the toxic gases, toxic emissions from a fire, or let emergency access from the interior. So these fireman knockout panels should be ideally fully tempered glasses, so that they would allow complete fracturing of the glass panels into small and safe pieces. Or else there are conditions, I think now in Singapore they are recommending the pivoted window panels for fire access panels. Of course, having talked about the pivoted windows as fire access panels, dedicated fire access only, the main problem you have to encounter is the water infiltration, because it is very hard to ensure very hard to prevent water infiltration in a pivoted window, because the gaskets and the beadings especially have to be very, very carefully articulated. Otherwise, you can allow the fireman to come in. Along with the fireman would also come water when it's when it's facing cyclonic conditions outside, right? Talking about glass, there's another trade-off we have to talk about: safety and sustainability. Now, sustainability is the double glazing or the DGU units we talked about. 2 planes of glass with a spacer, ideally 12 millimeter gap inside, filled with atmospheric air or inert gas is the ideal. And of course, you have a desiccated desiccants to absorb moisture there. This will be the best to ensure sound insulation as well as heat insulation, because the heat waves have to come through, pass through 2 medias, contrast medias, and in this there's a huge heat loss, and that ensures very little heat comes into the building. But at the same time, The problem is, as I said, these will be anneal glass unless you are going to spend astronomically and use tempered glass DGUs. Still, the tempered glass DGUs also will, once it's, if both the panels are shattered, then of course the internal external integrity will be lost. In terms of safety, one of the best bets would be to go for tempered laminated glass. But of course, as I said, you need to ensure then to mitigate the heat transfer from outside into the building, you need to have a low E coating, right? May not be as efficient as the DGUs, but in order to meet the requirements of safety as well as energy conservation, you might look you could look at tempered laminated glass along with a low E coating. Now these are all options, combinations and permutations which you can choose from, suitable for your need, suitable to your purse, suitable for the client's requirements, and of course to the conscience of the profession. Now we talked about the problem of safety and sustainability, and of course glass being used as a as an element of not only utility but also of expression. Now this is the Apple flagship store within the IFC mall of Hong Kong. You can see how glass is extensively used, not only as a support element but also as elements of a staircase, and not only as that, also the building skin here, right? And here we have the challenges which are peculiar to glass infills, right? Now we are not talking about stone infills, we are not talking aluminium infills, but glass only. Now it's a counterbalance between the thermal comfort and visual comfort. Why? Because the the conflict is when you uh, when you block the heat element coming in, there's a component of light also which is lost. Now, when you increase the shading coefficient by a low E coating, because shading coefficient is more related to to radiant heat as opposed to the what you call the U value, which is related to the conducted heat, right? Now, more than the conducted heat, here we are looking at stopping the heat waves coming from the radiant heat, and then the shading coefficient is increased by the introduction of a low E coating. But at the same time, it reduces the visual light transmission or the VLT into the building. So what do we have to do? We cut off the heat, but at the same time, we have to burn artificial lights within the building. Now it's a counterbalance between the power supply demands of air conditioning or the power supply demands of lighting. Of course, the power supply demands for air conditioning being superior, we would even do lighting, or we wouldn't mind investing on more lighting even when the external lighting conditions are better. Now, for an example is again the Apple flagship store on the IFC Mall Hong Kong. You can see this is a clear sunny day, but you can see all the lights burning within all the lights are on within the interior. And of course, when you go into the interior, you can see you don't see the sunny atmosphere outside. It is relatively gloom because the glasses have good are given a good low E coating that ensures a very good shading coefficient. Now, of course, the Apple being Apple, now this in Shanghai, even in sunny Shanghai, they would use the glazing as the entrance. Now it's almost like a trademark of the Apple flagship stores, right? That's the IFC mall in Shanghai. Earlier it was the Hong Kong. Now we talk about infill types in curtain walls. We are talking about glazing, but glazing needs to be controlled in terms of visual penetration. We talked about privacy, right? We talked about privacy and the need to expose certain areas when needed. Now, for that purpose, we have two types of glass in the curtain wall glazing. One is the vision glass and the other one we call the spandrel glass. The vision glass is used where you need to see outwards and you want to be seen from outside, right? Some of us want to be seen as well as seeing the other person on the other side. But there are things we want to hide, right? Things we want to hide are within the ceiling cavity. We have MEP installations, you have the air conditioning the diffusers, the extractors, you have the, the sprinkler lines which are within, you have the AC, if it's split units, so on, or FCUs, you will have the in and out chill water lines coming in, then you will have the back sides of the light fixtures that you could see. So many MEP paraphernalia goes within the ceiling cavity. Now, we don't want everybody to see that. So, since the curtain wall goes right outside the building structure, we need to ensure these areas, which are called spandrel glazing, would hide these unwanted things that we don't want the others to see. So, we use either translucent glass that comes in the form of what you call frosted glass or pin-headed glass, we call it, or else or sandblasted, or else we use what you call back painted glass, or you have another thing called the back pan, or it brings into the discussion a thing called the shadow box apparatus, right? So either you have a back pan within this the glazing in behind the glazing infill, or we make it a translucent or opaque glass, right? So that's the spandrel glass. Sometimes in certain areas, now if you look at this instance, it is the curtain wall hugs the concrete structure, and you don't want to see the concrete beams and the slab edges and the anchors that connect the mullions to the structure through this glazing. So you make this into an opaque or translucent glazing, so that this hides not only the structural elements but also the the MEP paraphernalia within the ceiling cavity. And some areas we do have what we call raised floors. If this had a raised floor, definitely even if there's no parapet wall or a perimeter slab that goes along, perimeter parapet that goes along, the raised floor and its contents also will be hidden by the spandrel glazing here. Now these are examples of spandrel glazing. That's the spandrel and the vision glass, and you can see the ceiling cavity which should be contained there. Another example of the spandrel glazing, now incorporating a rigid insulation or rigid fire insulation in the spandrel area to provide higher thermal resistance, because this is a preferable it's a preferable arrangement in my book, because this allows to ensure that the uppermost areas of the mullions are insulated against the spread of flames and their exposure to flame, because the flames could make the mullions weak at this point and the whole integrity collapses, is compromised. And then you can see how this the introduction of the rigid insulation ensures what you call a shadow box in this glazing, and then it makes it opaque, right? So you wouldn't see any of the compressed rock wool or the fire stop sealants that help to ensure fire compartmentalization. So this is that setup, and you can see another configuration. Here you are ensuring the upper part of the perimeter slab edge receiving the majority of the fire stop insulation, sorry, the rigid insulation. And in this instance, this is the more preferred method for me, where you use, if not both the surfaces, the upper segment and the lower segment, but at least the lower the segment immediately below the perimeter slab edge would have the rigid fire insulation, because this is the more critical part for the mullion's integrity, right? And this is the rock wool insulation, compressed rock wool, and the fire stop sealant that has to go even above the anchor joints, right? So this is what you see from outside, And these are more uh, uh, visual examples of how the spandrel glass and the vision glass would behave on the building facade, right? Here you can see up to the sill level, the spandrel glass is extended, and also the ceiling cavity is also ceiling cavity below is also hidden by view from the spandrel glazing, and ideally the perimeter slab bed should be coming somewhere around here, right? So although these visually expressed as different lines, these are not done for aesthetics alone, but of course you can make this part of the aesthetics. So talking about aluminium and the curtain wall, I think this is something I would like to stop and discuss, because uh, the usage of aluminium in our building industry is quite high, and aluminium is used for good reason. One is the low unit weight and the qualities of good weathering. It can withstand the tropical weathers, and the color, the fastness is good in terms of withstanding rusting, corrosion, everything. Aluminium plays a very superior role against other metals. But however, the relationship with aluminium is in curtain walling is rather a love and hate relationship, right? So it's like a human relationship where we have certain people with good qualities, magnificent skills, which make them really needed in our day-to-day activities. But of course, there are certain bad qualities in these people which make it very difficult for us to deal with. But still, since we have benefits and benefits by the association, we tend to tolerate the bad qualities and then still try to accommodate their misgivings or shortcomings in order to ensure those benefits are accrued for our usage. So there are 4 qualities in the aluminium uh, which I feel are mitigatory or kind of detrimental to the safety and security of the curtain wall installation, especially in terms of the heat resistance and the possibilities of deflection. But of course, we tolerate it because it can serve us in terms of low unit weights, which reduces the self weight or the dead load of the curtain wall, and better weathering against our tropical conditions. One of these 4 qualities is the low modulus of elasticity. I said it deflects 3 times compared to steel because it has 1/3 of the modulus of elasticity that is experienced by steel. So the deflection limits we need to be specified, whether it's wind-induced perpendicular deflections or dead load induced in plane deflections. And I discussed how these deflections could cause the breakage of glass panels and the glaze or the glazing infills being ejected off the mullion pockets. So we need to limit the deflection in order to control the movement of the curtain wall interior. So the inside space doesn't get increased and decreased with the periodic movements of this curtain wall. The next one is the high coefficient of thermal expansion. The coefficient of thermal expansion causes the curtain wall to expand and contrast within the span of few floors. So it expands and contracts, and it has, so by this phenomena it has to resist the relative movement against the main structure due to these expansions and contractions. So we talked about how the anchors that carry only the wind loads are slotted to allow movements, right? So the mullions could move even within the anchors to allow for this movement due to thermal expansions and contractions. And we talked about how even live load deflections at the perimeter slab edge and creep could be absorbed by this little flexibility we give. And then another one is the high heat transfer coefficient. Now this is if you look at aluminium, it's a good conductor of heat, right? It's too good that it results in high heat losses within the building interiors, right? So through the mullions, the heat losses could happen. Especially in our countries, we could get the external heat into the buildings, or in cold countries, the internal heating could go to the outer uh, uh, exterior of the building due to the heat loss. So what happens here is uh, we need to ensure that the HVAC costs are kept to a minimum. So to ensure this, we incorporate thermal breaks, which are used as thermal barriers between the interior and the exterior metal to reduce the conductivity of heat. But of course, these thermal breaks interrupt the overall I value or the moment of inertia of this mullion, so that the integrity is threatened slightly. The last but not least, the more serious effect is the melting temperature of aluminium is low. So it's a low melting temperature. It is actually in aluminium, it is 600 degrees. And you know, in a building fire, the temperature reaches more than 1100 in a couple of minutes. And what happens when aluminium reaches melting point? It ensures that the facade will lose its structural integrity, right? Within a short time, it would, once the structural integrity is compromised, then the fire could lick up the building in no time along the building exterior. And when you're using composite aluminum claddings, then what happens is the flanking aluminum panels could melt away, and it would expose the inflammable infills, which are mainly HDPE, and then you start a good old facade fire that run through the building much in a much greater speed. And that, of course, is something that the building designers will have to be very, very careful of. So we have two laws, the low modulus of elasticity and the low melting temperature, and the two highs, high coefficient of thermal expansion and the high heat transfer coefficient. All four are very detrimental quality to the aluminum curtain wall. But of course, as I said, there are paradoxes we have to live with, because we have to have certain benefits of the low unit weight as well as the weathering qualities of the aluminium. Now this is what I'm showing you here is a thermal break. You can see how the mullion as well as the pressure plate are detached or separated by this thermal break, which is of a different material, and then it, of course, it compromises the overall I value or the section integrity. And I think this is even a better image, which shows the mullion inside, the pressure plate outside, the pressure plate cap, and these are really the EPDM gaskets, which form outside, and of course inside you'll have the baccarods and the sealants coming in, and you can again see how the overall I value is compromised by introducing this thermal break. But of course, these are things that we'll have to look at. I mean, the compromises have to be made. You need to kind of make value judgments as to what qualities you expect from your curtain wall in terms of its structure as well as the heat conductivity. Well, we talked about the perimeter slab edge, how the perimeter slab edge needs to be a fire stop. The back pan, we talked about how the space between the back pan of the curtain wall and the slab has to be has to be sealed off against the migration of flames and toxic fumes, right? And it has to have non-combustible insulation at the the interior face of the curtain wall. We talked about mullions need to be wrapped with heat insulation or with fire mortar near to the ceiling joint to prevent the mullion from melting and spreading the fire to the floors above, right? And if that happens, what's the issue? Then the strength of the mullion is compromised, the glass infields will break, glass will shatter and fall onto the street. It will harm the pedestrians, the firefighters, the fire hoses, the fire engines, everything. And then it will leak up the building like this, and will start, it will cause fires on each floors, compromising the the principle of fire compartmentalization. And according to regulations, the engaged compartment, so you have to compartmentalize the spread of fire and smoke from the engaged compartment to the compartments beyond, and you ensure the fire rating of the floor slab. And if you look at the fire stop is an extension of the fire resistance of the floor slab. While the floor slab and this joint is should be fire rated, there's no regulation that tells you that the curtain wall itself has to have fire rating. Now, these are another paradox that we live with. Although the compartmentalization principle by regulation would ensure that the floors have to be fire rated and the fire stop has to be fire rated, but the curtain wall not being fire rated would compromise this principle. So these are points that as professionals, as I tell all of our professionals, whether architects, engineers, or quantity surveyors, we need to act according to conscience, look at the duty of care we have for the clients. Whether you have regulations or whether you don't have regulations, you need to exercise your professional opinion, exercise your professional integrity, ensure that you act according to your conscience to the full, to the maximum, and to ensure the interest as well as the safety of the client, whether the building, whether it's the primary user, the secondary user who's the visitor to the building, or even the tertiary user who is the guy walking on the street. So whatever said and done, these are issues that we will need to discuss, whether the in terms of the glazing and the regulations that govern the installation of curtain wall, right? So these are little examples I have brought in just to show how the perimeter slab edge could have the compressed rock pool and the fire stop sealant, as well as the rigid fire insulation behind the spandrel area. Another example, of course, here without the rigid fire insulation as this one, so that it creates a little shadow box effect here. The more preferred one is the right hand side. And another two examples where the rigid insulation goes above and below the perimeter slab edge, which is even more preferred, so that both the sides are equally protected. And these are a few examples with photographs. Now this is a mock-up model to show how the rigid fire insulation as well as the compressed rock pool is insulated and the fire sealant comes in. But the application of the fire sealant, the final one, is needed, which is marked in red, in order to ensure that the smoke migration is stopped, right? And these are a few more examples. I'll rush through these slides, right? And a few more examples to show the application of the fire stop sealant above the compressed rock pool. Then last but not least, we come to the maintenance and repair. Why do we have to do maintenance and repairs? Because the perimeter sealants are the last, they conform the first line of defense. There could be several lines of defense. So it is said that the weakest link chain is as strong as the weakest link. But if so although the glass remains intact, the mullions, the transoms, would remain intact. If the sealants and the gaskets give way, then you have a problem. Then you expose the weather sealants inside along with the backer rods which are within the mullion frames. Now, the typical service life of the external perimeter sealant will be between 10 to 15 years. And these need replacement, inspection, going to site, looking and feeling the joints and seeing. And sometimes this replacement need meticulous surface preparation. Now, even cleaning has to happen on a very safe and stable platform, so that we don't use arbitrarily use cleaning agents which de-anodize the anodized sections, right? So you have superior applications like fluoropolymers and fluorocarbons and so on, which are baked on coatings. But certain things like re-anodizing cannot be done in place, but they have to be protected by coatings, right? And to ensure that glazing seals and gaskets are intact, they need continuous meticulous inspection and maintenance. This is to minimize the water penetration. If water gets into the second line of defense, it would expose the frame seals. And then what happens is insulated glass seals could get wetted. And where what happens is, if the glass if the glazing gets exposed, especially the laminated glass, if it's PVB, then match over, what happens is the glazing starts, the laminated glass starts to get delaminated. Now, this is an internal joint. Here you can afford to have the silicon gaskets as well as the silicon-based structural sealant. But when it comes to the external frame, you cannot use that. You need to have between these, you will have the transom, the mullion, and the EPDM setting block, which would receive the pressure plate, and the EPDM gaskets that go in. But something that you don't see here would be the ATPDM setting blocks, the backer rods, and the weather sealants there. Now what happens is, if water penetrates here, then the weather sealant and the backer rod is exposed. Then what happens to the laminated glass? From here it starts to get delaminated. So you need to ensure the outer line of defense is always protected. To do that, we need to ensure workers can stand on very safe platforms, easy platforms to work with, like what we do here. So you need to have ensure worker safety at maintenance. Now, this is why I always show this example. When you see these louvers, you might think these are decorative elements. No, but actually within this set of louvers, we have installed 6 units of AC outdoor units, so that the workman can enter this compartment of AC outdoor units from inside the premises with a toolbox, very casually walk into that place, do the maintenance and go off. But of course, it's not the same in every place. I see so many AC outdoor units being installed in other buildings. Suppose this is the only way that the maintenance could be done, by hanging out the guy who's doing the maintenance as well, right? Now, if we have buildings such as these, if you are not careful about work, the maintenance worker, we might as well adopt strategies such as this to ensure the building cleaning and the the inspection of glazing sealants. For that, we do have now snorkels. We do have, this is called the octopus extendable snorkel, or mobile snorkels, which are also called cherry pickers. Of course, we don't pick cherries here with these, right? These are mobile platforms. Of course, we do have scissor platforms, temporary gondolas, movable gondola systems, right? As well as the good old David arms. Now, here you have the David arm, which is demountable, and of course you can adapt the required size and form of the service gondola, right? And these are the newer versions of David arms which coming, so that it's operatable from the service gondola itself. And now the gondolas come in different forms and shapes. The movable BMUs, what you call the building maintenance units, which could run on rails like these, or which could run along the parapet wall like that, or which are static like these ones. The arms, the boom itself could be swiveled maybe by hydraulics or maybe mechanically, right? And here you have the heavier ones. Of course, you need to ensure if it's a rail, these rails, floor mounted rails, the ones near the perimeter would always experience compressive stress, whereas the rails on the exterior, when the boom arm is extended outwards, it will be a tensile stress because this rail will be pulled out of the slab. So you have to have two sets of wheels. One is to have mobility along when it's going under gravity, and then another set of wheels that will ensure that while it is mobile, you can resist the the pull or the tensile force from the boom which is extended out there. So it is a job for the structural engineers. Of course, if you're designing a high rise, you need to ensure that the BMUs or the building maintenance units are also designed along with the structure and put it in the and added on to the building budget, so that there won't be last minute cuts. And of course, for different buildings, we do have different boom arms. The swivel booms we do have with the swivel attachments also come with them. So depending on the type of building, we have you may use this again a parapet wall mounted BMU. Here on the top rail will be a compressive stress, and here will be a tensile stress. So you have structural, we have to design accordingly. On this one, when the building does a little funny undulation, you need to have the gondolas with a counterweight, so the gondola itself could move into the building with the undulation, and the workmen can do their work without any problem. Now, well, you can have a matching BMU to match the expression of the building, just like this, right? Just like some of us, I see some of the ladies have been wearing these, since we have to wear these masks, some of them even match it with their color, with the color of their clothing. So this architect and the engineer thought they will match the BMU with the architectural language of the building. So this the telescopic boom of this building, company is, I think, Philip Cox, if I'm not mistaken, designed this telescopic boom as part and parcel of the building structure and the building expression. Well, when the booms are not there, we do have what you call the monorail. So on this rail, which is permanent, the gondola will be a self-winding gondola which will move along. It will have its own motor to take it horizontally and vertically, wind up and down. And the only thing is you need to have a place for this to hibernate, right? And now this is again a monorail. You can see when the building top is undulating, when we have a little funny shape on the top, again, rather than having the conventional David arms or the service or the BMUs, it is much easier to have a monorail that is sticking out of the building edge, top edge, so that the self-winding gondola could move up and down. Now these Petronas built in Malaysia, again the BMUs can move along the girth of the building and then could be folded back into place when they are not in operation. Of course, when nothing works, the good old Spider-Man and Marvel comics come into play. So the Spider-Man will have to come and do the trick by cleaning up the building facade. The final note will be on two buildings on the Shanghai Pudong area. One is the Jingmao building, which was done quite earlier, and it was there in 2004 when I came in, which was only shorter than the 101 Taipei. Of course, done in the same manner, just as an outrigger structure. Now, this building is a complete showman structure. You can see you have a 152-meter atrium. When you look down or look up, you feel dizzy. And of course, they do have glass bridges or glass floors that span the atrium. And whenever I see glass flooring, I feel like doing a little loading test on it, because people need to see whether these glass surfaces are safe to tread on. And looking at this building, you can see this outrigger structure, just like a bamboo shoot. That itself is a cleaning service operators nightmare, because you have so many jagged edges and so on, as if the architects and the designers had something against the building maintenance guys. But when I get onto the Shanghai uh, the Shanghai Tower and observe the top of this Jim Mao building, you can see how the architects have articulated, architects and the engineers have articulated the BMUs or the building maintenance units perfectly well with the building form, that you cannot detach them, the BMU and the railing tracks, from the form of the building itself. And these located in the right place and the right position, the equipment is geared to ensure that every nook and cranny of the building exterior could be cleaned up, and the glazing could be inspected, that they sit perfectly well into the structure itself. Now, these the structure during the evening, and these are the two BMUs parked side by side on the top, right? This Shanghai in the evening. And looking at this, another structure is the building with a hole in as we had this 911 incident. People were laughing that they thought that if somebody wants to fly a building into this, an airplane into the building, if the pilot wants to change his mind at the last moment, he would have this hole to fly through. But actually, it's not the case. But the architects had a fancy idea of articulating this building in a way that it makes the cleaning and the maintenance of the facade into a living nightmare. But at the same time, you will see how they had the good sense of incorporating a building maintenance unit system to clean every nook and cranny of this facade, which undulates on all four sides possible, right? So you can see how it undulates on the vertical, horizontal planes, and how it kind of leaves no straight line at all. I'm looking at this building from ground level. You can see how awkward the facade undulates. And of course, the two neighbors are not very different either. You can see the twisting Tower of Shanghai on one side, and the jagged Jinmao Tower on the other side. And this guy to have this crazy top is not much of a surprise, right? So this is looking at the two neighbors and this building. And we talked about these buildings. This is within this period, is 2015, if I may remember. Out of the first 5 buildings, these 2 buildings were there among the tallest 5 buildings, right? This guy was taller than 600 meters, while this the IFC tower, which I'm going to focus upon, was almost 500 meters tall. And looking up at this building, you could see how there are 2 little compartments or little galleries. One is a gallery on top, and of course later on you will see there's another gallery below. And then here the building is all about showmanship as well. You have this gallery up there, just about 500 meters above the city of Shanghai. You can traverse up there onto this gallery, and then what you do is you take photographs, and you take photographs from the floor slab, again glazing. So you have structural glazing that you can stand on, so that you can take photographs of the city below. Of course, that's the topmost part of the building. You can take images from the side, and then you can see they are literally standing on glazing. And whenever I see structural glazing, you are allowed to stand on it and take photographs, just to show that you are standing on thin air. If the glass collapses and if I fall, I would have been still tumbling down this building right down. Now you look right below this glass panel, and what you see there is this square object. This is Philip Cox is written on it, and it is a BMU. You can see how this, if you go down there and look at how this BMU is placed, I don't know whether you can see my cursor. This is the BMU I'm looking at from above. Now you get a close look will show the trade name Philip Cox, and you get into this gallery and have a closer look. You see how this is parked very unassumingly by the corner, and of course it is movable. Now this is the gallery below, and you see the telescopic boom, which could extend and also swivel outwards and clean every nook and cranny of the clean or repair every nook and cranny of this undulating facade. If not, it is these guys who really suffer because of our designs, and they will really uh, they may not be very happy with the architects nor the engineers who would design structures such as this. But that's why you need to have this kind of meticulous thinking. Now it's a movable BMU, telescopic boom with a swivel attachment and a very spacious service gondola that would move up and down. And oh boy. And then what we have here is how you see it parked outside this lower gallery. So you can see this BMU, and this is the lower gallery, this is the upper gallery. And having a second look at this building, that's the upper glass gallery from which you can stand and watch below, and this is the second lower gallery adjacent to which you have this BMU, right? So I'm going to, I think there's a little limitation on the time. I think we are approaching 8 o'clock. And you can see while you you can access the facades of this part of the building from this BMU. There are 3 more on the upper level, which could ensure that even the uppermost levels could be reached. The facade could be maintained from the service gondolas of these BMU units. So we talked about fire safety, we talked about the structural integrity of glazing or the facades, the curtain walls, as well as the other types of walls and fenestrations. We talked about not only the testing parameters, and last but not least, we talk about the aesthetics. Of course, I'm not going to dwell upon aesthetics. These are the commune of Menon on the French Riviera, closer to the Italian boundary. You can see these are individual facades that make a composite facade. So this commune or this township would have a composite facade that faces the water body, right? Just like that, it is now the Shanghai Pudong area. All these are individual facades. This is the IFC building and the Pearl of the Orient Tower, then the Shanghai Tower, the Peace Center, everything. It would make, again, the Pudong area itself makes a composite facade of modernity. Then on the opposite side will be the composite facade of the city's history that showcase the old interior. Now, last but not least, my final comment is that, so as much as the performance is important, this composite expression of a city, its identity, its people, the message it has to convey is also as important as much as our functional needs of keeping structural integrity, ensuring fire safety, as well as ensuring water tightness and air tightness of the building, etc. So, coming to the last slide, my comment is the building facade, of course, is a building skin, but while the skin has to be aesthetically palatable, let not the consideration of designing the skin be skin deep. So the consideration should not be skin deep while we deal with the aesthetics. So with that, I will wind up this presentation, and maybe we could start off with the questions and answers, or if any clarifications are needed. So thank you, and I will hand it over to the to Ishan, the moderator at the control stage.
Thank you, Doctor. Good evening, ladies and gentlemen. I'm Dilanti Langa. Since the time is running out, let's straightly go for the questions that we got. Doctor, first one is from Mr. Shevin. What are the recommended systems for buildings where close to sea? What are the recommended systems for building which are close to sea?
Recommended distance to the buildings. Of course, that's a very fantastic question. Only issue is now this relates to the coastal management plans as well, right? So the recommended distances, of course, if you are not looking at the facade, so we are deviating from the facade, but I like to kind of address that question. The closest, the distance from the sea, of course, to the building is measured in terms of the distance from the mean high water mark of the sea, or the furthest line of vegetation, right? The high water mark and the low water mark is determined by the ebb and tide, right? Now, this is related to coastal erosion as well as the protection of coastal habitats. So these, of course, if you look at tap into the CCD, or the Coast Conservation Department official website, it has the comprehensive coastal management plan from zone to zone. There are quite a lot of zones defined right around our island, and the strategic distances from which the building has to keep from the mean high water mark are all stipulated there. But of course, even the architect and the engineers could exercise their discretion. You need to understand these regulations are only prescribing minimum standards. So it's the minimum distance you give. But if you're sensible enough, or if you feel according to your conscience it has to be kept more, I would advise follow your instincts in that, but of course always abide by the regulations. For an example, I mean, there was an instance where late architect Turner Wickramasinghe and myself, I had the privilege of working with him in a hotel that we did at Veligama. The coastal management plan allowed the building to come close than 50 meters from the mean high water mark at that time. I'm talking about late 1900s. But of course, the architect was so sensible. He said, "No, we will set back the building as much as possible." Now, these at Veligama from the shoreline, so that we create an ocean park between the building and the seashore. And you know what happened is, when the tsunami came, this was the only hotel that was functioning in the southern seaboard, and because it was kept as further away from the shoreline and on high ground, that all the other buildings in the locality got swept away and got damaged. But this operated through the tsunami, and it became an operating platform for the tsunami rescue operations as well. So coming back to your question, don't only stick to the regulations, follow your instincts, go with your conscience, ensure that you do the best according to the best of your knowledge to ensure the safety and security of your client. Whether it's the client who pays you, so that will be the primary user, the guy with the money, or whether it's the secondary user who uses the building, it could be an innocent office employee, or the tertiary user who's a visitor who's coming in, or else even the most distant user, the guy who's standing outside your building. So all these users are your responsibility. By giving you a charter, whether you're a chartered architect or a chartered engineer, is given by the Republic of Sri Lanka, and it expects you to ensure the safety and security of all people, or all citizens of the Republic. So it is you are bounded by your conscience to the Republic of Sri Lanka, and not to the employer who pays you. So definitely you need to ensure that just abiding by the regulations, or violating the safety codes just because of the absence of regulations should not be done. Ensure that your professional knowledge and integrity is used to the maximum to ensure the safety and security of your building users. I hope I answered your question. Maybe a bit too lengthy explanation, but I would like to get on with other questions.
Right. Dr. Next section is from Mr. Pasan Heva Kandambi. When powder coating extrusions are lost when handling, are there any remedial measures?
So powder coating extrusions, is it?
Yeah, when powder coating extrusions are lost when handling, are there any remedial measures?
Yeah, it's a good question. I mean, if you look at anodizing, it's a simple procedure of a simple battery where you have the anodic components and the cathodic extrusions are bound by electrovalent bonds. This withstands abrasion in a very strong manner. Of course, the abrasion resistance of a powder coated extrusion may be limited as opposed to anodized extrusion, because the powder coating is done also in the initial process, the extrusion, the aluminum extrusion, and the paint particles are given a plus and a minus uh, charge in the initial stage when they are sprayed, and then until the entire extrusion is baked and heated, the two remain together because of an electrovalent bond. So the anode and the cathode stick together. And also there's a limitation in this thickness, and that is about 70 to 80 microns is permissible for the powder powder coating of the extrusion. It's not less nor more. It could be lesser according to the place of usage, but it is advisable not to exceed this the maximum micron thickness. Now, when this could be lost due to abrasion. Now, when this is lost, of course, remedial measures are very limited if you want to kind of remedy the issue while the coating, the extrusion is in installation. If you don't want to remove the member, then of course you need to contact the specialist. You need to get the in most of the time you cannot do a re-powder coating at site. So it has to be a secondary remedial measure where there are different service providers or different suppliers could come in with their own type of remedy. With either they will have their own type of primer, and then with that primer they will try to patch up the extrusion, but it is not the same powder coating that you will get. So the answer is in terms of remedial measures, there are remedial measures which could be done by the service providers or the installers, but in most cases it will not be the same as the initial powder coating.
Next question is from the same gentleman. Nickel sulfide impurity in glass cause spontaneous breakage in tempered glass. Heat soaked tempered glass could prevent this. However, soaked glass are costly than normal tempered glass. Are there any other tests to confirm tempered glass is free from nickel sulfide impurity?
Yeah, it's a good question. That's something I didn't mention. Yes, spontaneous fracture is prevalent in tempered glass. This happens in the secondary annealing process, actually. So in this secondary annealing, in the primary annealing process, there could be non-reacted nickel sulfide molecules or nickel sulfide ions, right? It's a charge. So this nickel sulfide ion gets frozen in the tempering process, and then when the thermal conditions are favorable, this nickel sulfide ion expands, and then it causes spontaneous fracture or spontaneous breakage. Uh, the only known remedy, of course, is heat soaking, as you very correctly said. The heat soaking is a mechanism where it's not a remedy actually. It's a selection process. It's if the nickel sulfide ion is embedded in the glass, you will not be able to remedy it, but of course to discard it, or else use it in a place if you know. Of course, the way to know is also to heat it up to a certain degree, the process of heat soaking, and then see if the glass fractured. If it's fractured, of course, you have to throw it away. It's in pieces, or else if it does not, so you can safely assume that the nickel sulfide ion is not embedded in your tempered glass? So the answer is, of course, from to my knowledge, of course, I do not. There are, I mean, there are no guarantees against spontaneous fracture of tempered glass, except for the process of heat soaking. And there are, I mean, there are mechanisms to remedy glass, like the pigmentation of the glass could be remedied in certain ways, like the excessive sodium lime content could make a glass greener because of when the glass becomes thicker. And companies like Pilkington, I don't know whether Asahi, Guardian, Saint-Gobain, etc. would have that, but this Pilkington, of course, is known to have this treatment of manganese dioxide to make it clear glass. Some people call it crystal glass. But those are aspects that could be remedied. But the detection of the nickel sulfide molecule is only through heat soaking from the standard practices in the industry. But I haven't come across any anybody who could determine whether the nickel sulfide molecules are within the glass except for this test. But I must again tell you, I am not a specialist in glazing or glass manufacturing. I will answer the questions to the best of my knowledge, but always an expert's view, the view of a glazing engineer or a glazing expert would be preferable in this kind of situation.
Right, since the running
I
time,
hope I.
since the time is running out, we'll go for one last question, I think. How this facade design changes when we have vertical gardens?
When we have vertical gardens, what you meant is whether the facade design is dangerous, is it?
No, not dangerous. How this facade design changes?
Changes. That's a
Yeah.
good question. Yes, right. Now there are so many vertical gardens which are in operation. I think even your flyer of this conference I saw, I was happy to see that vertical garden. It's also done in Clear Point, which is done by a close friend of mine and late father of a friend of mine, Mr. Milroy Pereira, where the vertical garden was actually a little external garden at each level. Now, vertical gardens do have, it has evolved as a science and a technique now, where you have either the twin supports of twin grids that support the soil media or the planting media, and whereas one would exclusively provide structural support, the second one will be allowing structural support along with the inbuilt drip irrigation system. And the way to secure the planting media and the biota, or what you call the plants, could be done in two or three. There could be numerous ways. One is, if it's the grid system, within the grid, there are allocations to hang what you call canisters. It could be plastic canisters that contain the soil media or the planting media, or else what you have this system called kangaroo pouches. The kangaroo pouch is a system where you have two layers of geotextile membrane. The two layers are sandwiched, and then the stitches are crisscross. And I don't know whether I could show you a little sketch. Sorry, I think it will be a bit hard to kind of sketch and show you. And then you open up little slits on each of these square compartments, and the soil media or the planting media is filled inside. So the planting is done coming out through this kangaroo pouch, so to speak. It's like the pouch of a kangaroo. And to hold it in place, you need to have the building facade itself, which could be of a sturdy structure, or a secondary steel structure that would provide structural support. Of course, in this system, you need to have a secondary drip irrigation system that is automated so that the watering cycles and the nutrient cycles could be ensured for the plants there. One thing is the green facades, these green walls ensure that the heat absorption by these by the building facade and the transmitter inside is also mitigated, and it ensures the heat is absorbed, and the heat island effects that are experienced in the cities are uh, combated in a substantial manner. It ensures that you have you provide the greenery, or you provide the visual comfort, or intimacy with the natural environment to human beings who inhabit the city. But having said that, the irrigation of the planting, the replenishment of the soil, uh, the replacement of the soil and the biota when needed, and the replenishment of the nutrients and the supply of water are all considerations that you have to make when you get into green walling. But it's a good question, and I wish I had enough time to talk about green walling, the detailing related and so on. And because I'm a fan of green walls, I have seen these green walls being initiated and tested upon by the Parks Board in Singapore, as well as what you call the Hot Park at Alexander Road, which pioneered this technology of green walling. And today I see that it's being spreading around the world, and gives visual and psychological comfort for so many. But I mean, we could even organize another session where we talk about green walls alone. So thank you for the question, and it really refreshes your memory. And if you need any information, I mean, uh, there are websites by companies like Zinco. Zinco is a German-based company which looks at green walling, green roofing. Then there's another Singapore-based company called Verditecture. Then you have the Singapore Parks Board itself, which is working with green walls, green roofs, green terraces, and even now looking at communal agriculture, not only on the vertical plane and horizontal plane. And you should also look at what we call green scrapers. Just like the skyscrapers, there are companies which now advocate urban agriculture in green scrapers, or just the skyscrapers which are dedicated to planting and of course planting for the manufacture, I mean, production of food crops, right? So these are all good technologies we need to look at, and maybe these are very much relevant to our context as well.
Right. Thank you, Doctor. Before winding up, if anyone is willing to have raise hand questions, if we can give one or two opportunity.
Sorry.
No, for the, yeah. It seems there is no raise hand questions, so we'll wind up the Q&A session, and for the conclusion, let me hand over the control for our task leader for public lectures, Engineer Ishan Ranganath. Ishan, over to you.
Yeah, thank you, Dylan. That's the end of the very interesting session conducted by Dr. Senaga Dharmatilaka, and we would like to thank Dr. Senaga Dharmatilaka for his dedication to the response scheduled in March and due to the corona pandemic, we were not able to conduct the lecture. So when the ISL is hosting online lectures, again after the we came into the normal activities conducted by the technical committee, and I gave Dr. Dharmati Senaka call and asked for conducting a online webinar. So he didn't hesitate 1 minute to agree with my suggestion, and he agreed to do the lecture. So thank you very much, sir, for your dedication and the modesty. And again, I would like to thank Mr. Narangoda, Engineer Narangoda, one of our past president of the Building Services Engineers Sectional Committee. With the help of him, we were able to contact Dr. Senaka Dharmatilaka. And again, I would like to thank ISL for hosting us for this opportunity to conduct a webinar, and technical team of ISL, and also we had more than 140 plus participants for today's lecture, and we would like to thank on behalf of the sectional committee all of you. Thank you very much for your patience, and no one has actually distracted from the lecture, and we encourage that appreciation, I mean effort from your side as audience. Then again, we would like I'd like to again thank Dr. Senaka for coming with this kind of practical and technical knowledge sharing with us all, and Dr. Arangod also, Mr. Arangod also. So we would like to wind up the session for today, and hope to see you again with this kind of a lecture in near future. Thank you all, and very good night to you all.
Thank you, Ishan. Thank you for having me. And
Yeah.
and
Okay,
take care, everybody, and stay safe, be safe, and be happy. Right. So thank you and good night.